I'm Sanoga Frank. I'm going to present on orthogonal multiplexing empowered by deep learning. Orthogonal multiplexing is the ability for signals or light fields to be fed into a multiplexer. Then that multiplexer propagates the light fields, the many light fields, onto a single transmission medium, and that single transmission medium is again connected to a demultiplexer. That demultiplexer is normally called the speckle output. The speckle output performs the demultiplexing part, as we shall see from this presentation. Now, non-orthogonal optical signals have characteristics, and these characteristics are they have the same amplitude, the same frequency, and thus the same polarization and the same phase. So we shall see that these ones, they play a role in the orthogonal optical multiplexing. There are parameters that are used as far as the optical multiplexing is concerned. So the non-orthogonal multiplexing the non-orthogonal multiplexing light fields, or the non-orthogonal light fields, are propagated over an MFP, an MMF. An MMF, it's a cable, a mud fiber cable that is used to propagate these light fields up to the receiving end. Now, why is it that non-orthogonal multiplexing is used? It is used because of the pitfalls or the problems that existed in the orthogonal multiplexing. These problems are the division mechanisms, or the breaking nature of the orthogonal signals are the one that brought about the invasion of the non-orthogonal optical multiplexing, because this one had the problem of the dividing. As you can see, optical multiplexing uses techniques of frequency multiplexing, SDM, FDM, and so on. Now, this diagram here shows how the non-orthogonal signals fail to reach the destination by use of this transmission matrix here. So, but when we use the neural network, we shall see that the non-orthogonal signals reaches their ultimate destination. They are being multiplexed, then propagated onto this MM cable, and then now there is the single shot. The single shot intensity is used to pick up this signal and then propagates it to the neural network. So this slide explains what I'm from explaining. So multiplexing involves transmission of information through an MMF, including general scene images. We shall see how general scene images are being fed into the neural network, and then that neural network is trained and performs a classification. Now there is this function here, this relationship here. It is used to map. It's a many-to-one relationship. It is used to map the many non-orthogonal optical light fields to one to be propagated onto an MF. MMF cable, and then resulting into a single speckle output, IK. So a well-trained R node, R theta is the relation matrix, the relation expression which are from it showing is this one here. So when it is well-trained, can be used to to approximate the relationship between the speckle output and the many input signals or light fields from the input side. The neural network relies on this relationship so that the whole process of the classification of the signals or the classification of the input pictures takes place. So this neural network uses the training data, and this training data is the training data set is obtained and they are corresponding, and with respect to their corresponding wavefront. This data set has the parameters used to train this neural network. The structure of neural network it consists of the fully connected layer, and it has the convolution layers. Then it has the reuse net. Now the X layer is used to enhance the fitting and generation of the neural network. Then the convolution layers are used to because the convolution layer constitutes of residual neural network and convolution neural network. These ones are used for down sampling and up sampling. Then the skip connections are used to enhance the generation-free propagation of data on the network. Now, these are parameters that are consistent within the light fields that are fed into the neural network. The parameters are amplitude and phase dimensions. So the inputs are signals, light fields, and then it results into the output of 4 matrices containing, because we are inputting images, or we are inputting the attributes of that signal, which containing the phase and amplitude information. This information is successfully encoded and decoded by the neural network when it reaches the neural network end. Now, this diagram here shows how the input images of different polarizations with respect to amplitude and phase dimensions are being propagated onto the medium, and then the SLNet is introduced here. Now, this SLNet is the neural network here, SLNet. It performs a number of operations here within here, including the activation function. It uses the LELU activation function. The activation function performs operations on this by number of convolutions, because we have seen the convolutions here. And we see here there is the skip connection concatenate the signals, and then the final output is generated from this neural network here. So when the two light fields are being subjected into the neural network under different polarized being subjected to the neural network, so the performance of this network is seen to be 0.97 across 100 epochs. These are the number of iterations that can be done. Now, this 0.97 is retrieved by what we call the partial correlation coefficient, PCC. And also there is what we call the structured the SIM, structured similarity index measure. It's also it is also it's a measure that used to retrieve the performance to show the performance of the model. So here, this is the curve that shows the signals that are being fed. The four light fields that are being subjected into the neural network under different orientations or polarizations. And you see that when the iterations reach 100%, you see that the performance of this model really shoots up to 97 and something. This is the 3D simulation of this curve here. We see here the different polarizations, dimensions of the signals being fed into the system under the different polarizations, the different dimensions of magnitude and phase. So we see how the SLNet performs with respect to labeled data. 4 grayscale images are being multiplexed at the same polarization, and then they multiplexed using a single speckle output. Structure similarity index measure, I talked about that. It also works with the same functions, or they are used to retrieve the fidelity, which is the score, the performance of the model here. So here, this is the diagram that shows the input images and then the output image. It shows the relationship, what the SONET output with respect to the ground truth. The ground truth. So these images are fed into the SLNet, and then the output is this. So you see that in figure here it is over a 1 meter cable. So this is the performance of SLNet on the same data set, but for the same input data with respect to the 50-meter cable, optic fiber cable. Now this is the performance of the SLNet with respect to unseen data that has been. This is the evaluation data set that has been which the model or the neural network has not seen over a 1 meter MMF cable. So we see the performance results to the average performance of the model is the 98%. So this shows a successful non-orthogonal optical multiplexing over an MMF cable powered by deep learning, utilizing a single MMFP up to 5 optical degrees of freedom. So applications, challenges, we see that the performance of the model depreciates as the cable increases in length. Applications, it is used in super image resolution and anomaly detection. It is also applied in enhancing high throughput MMVs for communication and information processing, thereby improving internal capacity in optical communication systems. It is also used in feature selection. Thank you.